This is going to be a video explaining some of the basics of natural deduction that we'll be doing in Chapter 7 as a way to assess the validity of an argument without having to make a truth table. And so the way this is going to work is that, like we did in Chapter 6, you're going to translate an argument into propositional form if it already isn't in that form. And then what you're going to try to do is prove that whatever that conclusion is must be the case only using the premises in that argument by using rules that are kind of like rules to a game. We're going to learn that for particular kinds of statements, if those are in play, there are rules we can use to turn that statement into something else, and our goal is to eventually get to the conclusion of the argument, that is, have that appear using the rules from the premises in that argument. So work through this and maybe it'll be a little bit clearer by the end what that is supposed to mean. Okay. So as I just said, this is going to be a method consisting of using sets of rules or inferences to derive either a conclusion or a series of intermediate conclusions that are going to link up with the premises of an argument and eventually get us to that stated conclusion that we want, proving it. Okay, so here is an example of what a proof might look like. So here I have this argument, and note that for all the arguments we're going to see here, the conclusion of the argument is going to be distinct. They're going to put it on the right, and it's going to be preceded by this backslash, which lets me know this is what I'm trying to get, and this is what I should leave out of my argument, essentially. I'm not going to put that in there. Okay, so if I have not A, and if not A or B, and then 3 I have if A then B, what they've done here, right, so their move was they're trying to get not A to yield, well, it is the case that A then B, right? So imagine that was the argument you were given. Somebody says, here's the argument I want to show you. Not A, that's the premise. Therefore, if A then B. Here's how they would do that. They added to line 1 here, or B, using a rule called addition, which says that for any line that I have in my argument or proof, I can add via disjunction anything I want, because disjunction says at least one of the parts is true. So if in my argument I already have a line that's true, like this case not A, which is assumed to be the case, I can add literally anything. I could add or B, or not B, or if B then C, all sorts of stuff really. So now that I've got that, I have this line, which is an addition to my proof at line 2, not A or B using one addition. And then at line 3, I get if A then B by using this rule called implication, which lets me turn a disjunction with a negated part into a conditional. And actually it lets me turn any disjunction. A part doesn't have to be negated into a conditional, you just have to change something. But I've used that rule on line 2 to get this conclusion, and I'm done, because that's what I was looking for, if A then B. This is another example of an argument if I'm trying to get to G, and I've got these two claims. If F then G, F or G are the two lines that I have, and I want to get to G, there would be a way to get this to this G point using proof rules, which we'll go over later. Okay, so I want to talk about these first four rules of inference that are given in section 7.1, and these may be the first 4 because these are the ones that commonly show up in most arguments that we're going to see people make or that we're going to encounter in our work. And this first rule, really important, is called modus ponens. What it says is that for any conditional I have, if P then Q, and it doesn't matter what these letters are, if the first part, if the antecedent is true, then it must be the case that the second part or consequent is true. So if I have in my argument a conditional and I know that the antecedent is true, I could automatically assume then, add as a line to that argument, the consequent. It must follow via modus ponens because this is a valid argument form that always works. If these two things are true, this must also be true. Okay. And so these are just some complicated examples of what that looks like. Like if I had an argument in which these were the lines that I had, if not F, then it follows that G if and only if H. And on another line I have not F. Well, then I could also conclude on a new line in my proof if G if and only if H, because that was the second part of this conditional, and I knew that the first part was true. And so real quickly I want to talk about something here. That when I say the first part is true, it doesn't have to be non-negated. Like it doesn't have to be P without a negation here. All that means is whatever is in the first part, I have somewhere else in the argument. So if I want not F to be true, I need not F someplace else in the argument. That's what it means for the antecedent of this conditional to be true. I don't want F, I want not F. And then once I have not F, via modus ponens, I get G if and only if H. Same thing here. I've got this complicated conditional that says if A or B, then it follows that not both C and D. And another line in the argument, I have A or B. Therefore, it follows the consequent, the second part, not both C and D. So you're kind of just following the arrow. Once you get the part in front of the arrow, you can conclude whatever the second part is a new line in the proof. Modus tollens as a rule is related to modus ponens. That one says if I have a conditional and I know the consequent or the second part of my conditional is false, well then it must be the case that the first part is false. So I have a conditional, the consequent is false here. That means I could add as a new line in my proof, not P. The antecedent would be false. And here are some more complicated examples of what that would look like. So first one here, I've got if it's the case that D or F, it follows that K. And another line in the argument I have, well, K is false. So the consequent is false here because it was K, not K makes that false. Therefore, the first part must be false. So I negate the entire antecedent. It's not the case that D or F. This one's kind of wonky looking, but it's the same deal. If I have, if not G, then it follows that not either M or N. And at some other line in the argument, I have not M or N, essentially this negated. So this claim made false looks like this intermediately. Later on, we'll learn you can cancel these out with double negation. If there's two negations out in front of a claim, just cross them out like they're not there. Same thing, that would mean this thing is false because here it's negated, here it would be not negated. And then I would get this antecedent negated as my output. So the antecedent needs to be negated because this part was false, therefore this part's going to be false using modus tollens as a rule. So what I would get as an intermediate step is not G, and then eventually I would use double negation to just eliminate those, and what you end up with is G. Right. Hypothetical syllogism, this one's interesting and requires a little bit of anticipation and making sure that you're tracking conditionals in your argument. So if I have a pair of conditionals that share a common factor as the consequent of one and the antecedent of another, you can build a conditional that goes from here to here. So if P entails Q and Q entails R, it must be the case that P entails R. So if I have two conditionals, they share a common symbol as the consequent of one and the antecedent of another, I can build a new conditional linking the other parts, like I've done here, if P then R. And it doesn't matter if things are negated or whatever, so long as these are common factors that are shared. So here's some examples here. If A, then it follows that D and F. If D and F, then it follows that not H. Well, then it will follow that if A, then not H. What I have here is my conclusion. Over here, if not M, then it follows that R then S. And if C or K, then it follows that not M. Well, notice here, this antecedent is the same as this consequent. I'm going to have to do something a little funnier in this case, right? Here I want it if P then Q and then Q then R. So I'm looking kind of at this one as my first. So if C or K yields not M, and if not M yields R or S, then it must be the case that C or K yields if R then S. Right? That's what I get here. So the order on this is flipped from the example I give, but it's the same thing. If I have two conditionals that share a common factor as the consequent of one and the antecedent of another, I can build a conditional between the other parts, which is what happened here. Right. Then the last rule we get in 7.1 is disjunctive syllogism. That says if I have a disjunction and I know that one of the parts of that disjunction is false, well then the other part must be true, because a disjunction says at least one of the parts is true. So if one part's false, that forces the other part to be true. So if I had if P or Q and I knew that P was false, well then I could add as a line or assume as true, Q must be true. More examples of this. So if I have U or not both W and X, and I know that U is false, well that means one part of my disjunction is false, so the other part must be true. And for this to be true, I need exactly this, not both W and X. Don't ignore that negation. That needs to come with it. Same thing over here. I've got this disjunction, E or F, or if N then K, and I have not either E or F, so this part is false. Right? And I need it to look like this. If it was not E or not F, that would not be this part false, and I couldn't use disjunctive syllogism. I need this entire thing to be false on this side, and then I can get the other side of my disjunction, which is what I've done there. Okay. So This bit about substitutions I'm going to close with here for this video is important. I've kind of mentioned it along the way. The idea is that when you're applying these rules of inference, they don't need to look exactly like the first examples we get. So, and this you've already seen, just more specifically, if P then Q, and I have P, then it follows that Q. I should think about the modus ponens rule, which is what this is here, as if I have a conditional, and I know the first part of that conditional is true, then I get the second part to be true as well. So here, if I have if not A, then B, and I know that not A is true, which looks like not A, so I have the first part of my conditional, then automatically I get the second part, B. That's what I could add as a line in my proof here at 3. It doesn't matter that these are negated or whatever, it doesn't look quite like this, but it's good enough. Because the rule is really only about what I can do with conditionals. When I have the antecedent of one, I get to conclude with the consequent. More complex example we already saw, same deal. Doesn't matter that this doesn't really look like this because it's got these nested parts. What matters is that it's a conditional. I have the antecedent. I get to conclude the consequent using the modus ponens rule. Last thing here, premise order doesn't matter, as we saw in one of the earlier examples with hypothetical syllogism. This is still a valid case of modus ponens, even though it's not conditional first and then antecedent. All I need is a conditional, which I have. I have the antecedent of it here. Therefore, I get to conclude with Q. That's all I need. The order is irrelevant for getting this conclusion because I have the parts. All right. Common strategies here for constructing a proof involving the first 4 rules. And this is something you're going to use as you go throughout this particular section. The first set of 4 rules you're going to get in 7.1 and the exercises for that are going to be pretty simple in how do you get to the conclusion because there's not a whole lot of rules in play. But by the end of this, we're going to have something like 12 or 14 in play. It becomes far more difficult, and then you've got to have a kind of strategy for approaching the proof to save yourself some time in getting there. Because proofs, unlike with truth tables, you can do them in lots of different ways and get the same result. You could have a proof that was 10 lines that you might have been able to do in 5. Both of them may work, but one of them will save you more time. So my first tip is always begin by attempting to find the conclusion in the premises. If the conclusion is not there in its entirety, look at the main operator of the conclusion, and that's going to provide a clue as to how the conclusion should be derived. So if I have an argument, and I'm trying to get to this conclusion, and I notice that conclusion is already in the premises someplace, like it's nested within a conditional or something else, that gives me a clear strategy for how I need to go about trying to prove it. If it's not there, I need to look for that main operator, and then that's going to give me an idea about how to do it. Tip 2, if the conclusion contains a letter that appears in the consequent of a conditional, right, consider obtaining that via modus ponens. So if I have a conclusion, and I know that one of the parts of that conclusion is the consequent of one of my conditionals, I should be thinking, I bet modus ponens gets used. I need to find the antecedent of that conditional so I can get to this consequent, which will help me get to the conclusion that I'm trying to prove. If the conclusion contains a negated letter, and that letter appears in the antecedent of a conditional, right, now I should be thinking maybe modus tollens here, because if I've got a negated letter in my consequent, and I notice that that letter is not negated as the antecedent of a conditional, well, if I can get the negated consequent of that conditional, I could go back via modus tollens and get that negated part as my antecedent. If the conclusion is a conditional statement, consider obtaining it via pure hypothetical syllogism, because at this point, that's the only tool we have for building conditionals, is using hypothetical syllogism to get us to a new conditional claim. And if the conclusion contains a letter that appears in a disjunctive statement, consider obtaining that letter via disjunctive syllogism at this point. And later on, we'll figure out how to use addition to also build disjunctions. All right, this begins the section for 7.2. I'm going to end this video here and do this as a separate video.